Okay, let's start. Questions? Questions on PSET, questions on design assignment? Anyone started looking at a design assignment? Okay, don't wait until the end because you'll run into trouble. So just because based upon the type of questions I'm getting on the PSET, I think many of you will find the design assignment hard, so start on it sooner than later. PSET tomorrow noon, and that's going to be the hard deadline, so just make sure to get it in. Let's see. So if okay, the other thing is many of you decided to skip last Wednesday's lecture. So you saw my email about sort of don't miss it because today's lecture is probably going to be problematic for you if you didn't take the time to go through the material. The other thing is I decided that instead of penalizing, I'm going to, you saw my email that we are going to start having these quizzes, which are extra credit quizzes. Okay, so it basically means once I have the grading curve done, whatever is your extra credit stuff that kind of gets piled onto it. Okay, so we'll just do it that way. Pick up your midterms because we do shred the midterms once the course is over. So quite important. I think most of them are still with us. TAs have been carrying them to their office hours. Currently, they are with me. You can come right after the class and pick them up, or again, office hours tomorrow. Paul will hand it over to him, and again, sort of try to pick it up. Okay, so very brief recap of what I had started doing last time around, which is when we have very complicated systems, complicated sequential systems with lots of states, then instead of thinking of them starting as a finite state machine, we start to think of them in terms of what I called as Datapath FSM, and kind of the idea is that we start looking at their next state function and output function not as truth tables and kind of combination logic and all, but really a little bit like the way we think of software code. So I'd gone through some examples of counters, and we had actually also gone over this example of the timer, but just wanted to recap. So imagine we are trying to make a timer module, and a timer is kind of like what you apps on your phone or kind of timer devices that you have for timing races and all, where kind of it's a device where you load a value into the timer and then you let it run, and when it hits 0 it buzzes or something like that. Okay, so and meanwhile we can reset the timer at any point, and so imagine that this done signal is when the timer counts down, hits 0, it buzzes. Okay, so in something like this, since my timer may have too many bits, like maybe a 32-bit timer for example running on some fast clock, it would be way too many states. So instead of thinking in terms of an FSM, which would basically be essentially impossible, we think of next state function and output function in symbolic terms, kind of the way you would write in a program. So in this particular case, the next state function, essentially we begin to enumerate what happens under different conditions. So it's basically saying if it is reset, then next state is 0. If it's not load and it is done, then next state is 0. So essentially we have hit the state 0 and we are not loading a new value. Okay, so the load basically corresponds to when we set the timer to some particular value. If it is not reset and there is a load asserted, load is 1, then next state is set to whatever we see in the input. So this corresponds to feeding in some sort of a time value into the timer. And otherwise, next state is state minus 1. Okay, so this is how you might, if you were to be writing these things in software, this is how you might want to would write as well. If on the other hand we were to write it as an FSM, we certainly could in theory, but the number of states in our system would depend upon number of bits I have in the state variable, because I have, so if the state is 32 bits, then I would have 4 billion sort of bubbles in my FSM graph. So this is a much more compact way. And likewise, the state transition table, if again n was 32 for number of bits in the state, it would have 4 billion rows, again impractical to do. So this conveys the same message as those other formalisms do, but they are doing it in terms of kind of data manipulation we are doing on these. So we basically begin to use notation and syntax, which is more like a programming language. On the output side, it's the same story. So we have only 1 bit output done, and basically done is high when the counter has gone all the way down to 0. So we basically are trying to detect that we are in the state which is all zeros, and that syntax out there, which is basically saying, so each one of the bit, we are ORing them, and we are basically saying that the ORed version is 0, so we have to take a complement of that. And given any problem, again, drawing upon last time, we saw kind of a basic structure emerging again and again, which is there was a state register, and that state register is updated. If you kind of go back out here, each one of these clauses is basically giving me a next state. Next state is equal to something. And depending upon which condition is true, different clause is triggered, and that corresponds to a multiplexer. So essentially, we see that there's a multiplexer in front. Which input of the multiplexer is selected depends upon some combinational logic in general. And there are different possibilities out here. So in the next state could be set to 0. Next state could come from an input, and next state could come from the current state minus 1. Those were our 3 possibilities. So you see a multiplexer, which is a 3-input multiplexer. You can think of it as maybe a 4-input multiplexer with 1 input never being activated or just hidden. And then our select logic basically takes the relevant input. So if you see out here, again in the previous slide, these different conditions clauses, they depend upon the signal reset, they depend upon the signal load, and they depend upon the signal done. So what you see out here is I have some combinational logic which takes those 3 signals and then generates the one-hot code which is needed by this multiplexer. So any design of this nature basically boils down to then a multiplexer sitting out here, some combinational logic which takes all the relevant signals and then generates the one-hot code, and then you may have some logic in front out here which corresponds to handling of different cases. So we had seen counters, various kind of counters last time. We had seen this timer, and pretty much anything. Most problems can be kind of cast into this form. State register is being updated according to different choices, and the choice is decided by this kind of a logic, which is what we have called as the select logic. And then you would have an output function which corresponds to, which will take the current state and may take some of the inputs, not in this example, but we may have an output function which also depends upon some of the inputs. And in this case, all we are trying to check is that count is all 0. So there is basically an equality module out here which checks whether the output of the state register, which we call as a count, whether it's 0 or not, and if so, then that's the done signal. So, so this lets us. So for these kind of problems, we never draw the FSM, and there is no hard and fast division between which problems you should do starting with an FSM graph and which problems you should do starting with this kind of an approach. What is a data path FSM versus what is just a standard FSM is often a matter of perspective. Probably one thing certainly that if you have way too many states, then drawing FSM is an impossibility. And the other thing you would see is that when we start dealing with stuff where my state kind of begins to look like data variables, things which I'm adding, subtracting, multiplying and all, then data path FSM is perhaps the way to think about. Whereas if on the other hand, my state consists of a bunch of bits and they're just independent bits, okay, they do not form an arithmetic entity, then it's probably better to think using the methods that we are exploring in the current PSET, for example. So when you look at the problem, you would kind of will have to decide which way we have to go. In some cases, part of the design may be as a Datapath FSM and part of it may be just as a standard FSM. And that would be kind of the next thing that we are going to look at pretty soon in just a couple of slides. Another example, which I had also covered last time, was a shift register. So shift register is a module which basically shifts bits. Okay, so essentially what is happening out here is that I have, let me just kind of jump to the next slide out here. So what we have is we want to imagine I have a module which outputs n bits, but I load that module serially. So there is a single wire coming into it on which I send bits one after another. So the input is a serial port. Output is a parallel output. So if I want to load 32 bits, I'm going to feed the 32 bits one at a time on a single wire. They get accumulated into 32 bits of flip-flops, but then they are output in one go. So, and then there is a reset signal which resets in. So the module has a 1-bit input called SYN for serial input, and it has an output which is n bits. N could be very large, and I have a reset which resets everything to 0. So in this particular case, when I have reset, next state is 0. Next state is a n-bit entity, and again n could be very large. Otherwise, the next state, so what's happening is I'm feeding data bits one at a time. So the next bit which is available on this 1-bit input SIN, that needs to go into the least significant bit of my state register. All the other bits of the state register have to move up. So that's what's happening out here. This notation, what it is saying is that the n bits of next state are such that the upper n minus 1 bits are what used to be the lower n minus 1 bits. And whatever was on SIN now enters into the least significant bit. Okay, so if, for example, I had 8 bits of state register, then so I have bits 0 through 7. So what's happening is that in the next state, bits 1 through 7 are what used to be bits 0 through 6. So I've shifted them. And the new bit 0 in next state is coming from SIN. So I'm kind of feeding things in one at a time. I think I have a diagram which probably sort of shows it better. So this is my state register, n bit of state register, and see how the way I have wired things out here. What was bit 0 is feeding into bit 1 out here. What was the next to the most significant bit is now the most significant bit on the next state side, and whatever was on SIN is what becomes bit 0. So it's just a matter of wiring out here. And then I have a multiplexer which basically handles the two cases I have, shift or reset. So that could be, so in this particular case, my select logic is trivial. I just use reset signal. And so if reset is asserted, then I feed all zeros. If reset is low, then I feed the shifted version of state to be the next state. And my output in this case is again trivial. It is nothing but the state itself. So that's a shift register. You can now imagine versions of it where I can say shift by a different amount, shift the other direction, all of those things you can imagine. So you could imagine a shift register module where I can control how much you are shifting by, shift by 1, shift by 2, so how many, where the bits are going, and whether I'm feeding stuff from the MSB side or feeding stuff from the LSB side, all kind of variants, but they'll all follow kind of the same basic strategy that write the pseudocode and then map it to logic, multiplexer, and a state register. Questions?
In this specific instance, if you only wanted to shift by 2 in that specific direction, is there any reason why you would put a mux instead of just putting a reset capable state register?
You could play games with a reset capable state. So in this particular example even, you could imagine that instead of doing it reset this way, if I had a flip-flop which had a reset input, I could have used that directly. Okay, you certainly could. But in a way, it's sort of hiding the fact that a reset capable flip-flop usually has a multiplexer inside and doing this anyway. Okay, so this is just making it more explicit. So if you recall last time around, I had shown how you can construct synchronous reset, synchronous or even other kind of flip-flops, T flip-flop, JK flip-flops, all out of our sort of basic D flip-flop. So this is our basic primitive. Everything else is wrapping around it. And sometimes we take this basic primitive and some wrapping around it and give it a new name and can begin to use that. So in many cases, you may find a shift register or this kind of serial to parallel converter as a library module, but this would be under the hood. So the other thing, as we are seeing, is that just like when we were in combinational case, using our primitive gates, we built up modules like encoders and decoders and stuff like that, and then began to reuse them as our components. The same thing which is happening out here, that things like counters and timers and all are often available in libraries, and you use them as they are, okay, without kind of worrying about their underlying detail. So again, in problems, I will tell you, you have this available. Like sometimes I say you are only allowed to use D flip-flop. Other times I may say, imagine you have a timer available to you. So kind of depends. And in real life, also the answer depends upon what you are designing. So if you are in a chip design industry, usually you work with gates and flip-flops. You do not get to see these more complicated modules. On the other hand, if you are designing using at the board level, you might find entire chips which do timer functions and all, and you can kind of design using them. So you may see both kind of things depending upon the type of design you're doing. Okay. I think this was also an example which maybe I had covered, I don't recall, but this is a more sophisticated shift register. So it's a bi-directional shift register. So what we want to do out here is that I want to shift left or right. I want to control that, as well as, so if I'm shifting left, the serial data is feeding into the LSB. If I'm shifting right, serial data is feeding into the MSB. So again, I have a 1-bit wire coming in. I have n bits of output. And depending upon whether I'm shifting left or right, I kind of feed the data coming in from one side or the other side. And I have a load input, which basically immediately sets the output to some n bits of parallel. So what I have at this stage, if I were to draw this thing out here, I have a module, a register, which has n bits of output. I have n bits of input. I have a serial in, and internally what is happening is I am storing these n bits into a register, and SIN can feed from bottom, and in which case I'm going to be shifting up, or SIN can feed from the top, in which case I'm shifting down, left or right, basically. And that is controlled by left and right, these two inputs. So which direction I'm shifting and where am I feeding this 1 bit of input, whether I'm feeding it at the bottom or at the top, gets decided by these controls out here. So let's imagine left is shifting top, and shifting right is shifting bottom, for example. So again, if we were to try to do it with FSM, it would be insanely hard unless the n was very tiny, because whatever n I pick, all possible values can occur depending upon the inputs I'm getting. So if n is 32, in this case, all 2 to the power 32 possibilities exist. So drawing an FSM is essentially impossible. So we think in terms of the pseudocode. Now, the pseudocode out here for output function is relatively straightforward. Output is whatever the state is. It's the next state function which is tricky, and we have to again list all the cases. So if reset is asserted, then next state is 0. If not reset but left is asserted, then next state is shifted by left. So it's much like the previous example. If reset is not true and left is not true but right is true, then next state is shifted in the other direction. So if you see out here, what's happening is SIN becomes the MSB of next state, and what used to be the upper n-1 bits of the current state now are the lower n minus 1 bits. And then finally, if reset is false, left is false, right is false, but load is true, then next state is equal to in. And last but not the least, otherwise we just hold the state. Okay, we don't do anything. So in this case, left gets priority, reset gets the highest priority, then left, then right, then load. So it's a one hot code type control that is happening out here. And the circuit in this case begins to look like, again, going back to our model, I have the state register, I have a multiplexer. We see 5 cases out here. So you see a multiplexer with 5 possibilities out here. One is just loop back, which is hold. The other is coming from input. Another one is shift right by 1, shift left by 1. How many gates will these guys use? 0. Okay, remember, this is wiring. SIN naturally needs to feed to both of them because they have to feed out here. And then I have this combination logic, which is going to take reset, left, right, and load, everything that was appearing in these condition clauses, and generate the 5 one-hot codes out here. This multiplexer could be implemented in a variety of ways. One way might even be using the tri-state buffers, for example, that we saw earlier in the course. And then my output is nothing but whatever I'm seeing out here. Okay, go ahead.
So if reset left, right, and loader, if none of those are set, then we're in the 4th position on the mux and just holding the value.
Say it again. What condition?
If none of reset left, right, or loader set, then we're in the 4th position.
Then we are in this position. Yeah. So that's the otherwise clause out here. Okay.
Is it up to us to determine? So let's say left and right were both high. So you, according to this, we would shift left.
If left and right were both high, then left is takes priority.
If it's not defined, if it's not defined in the top.
Well, it was kind of implied by the order out here. Yeah, but that's the, if that's all I gave, then it's a valid question for it to ask which one gets priority. Okay. So yeah, so there's, I mean, I'm taking a little bit of a liberty out here, so it's just order was dictating things out here. Okay. Any other question? So same pattern again and again that we are seeing. Put a state register, put a mux in front, some logic at the input side of the mux, some logic at the select side of the mux, and in general, some logic at the output side also. Okay. So, go ahead.
If we wanted to actually simulate this FISM, you said it would be more complex if we were doing a large.
So for something like this, FISM is out of the question,
Okay.
right? Because FISM thing is it lets you deal with FSM graphs. And for these kind of things, FSM graphs are too huge. Okay, so you cannot use FISM. So for something like this, Verilog is usually the starting point. Okay, or as we will soon see, you split the design into two. One can be designed using FISM, and the other could be designed at a lower level. So we are just going to transition to that shortly. Any other question? Yeah.
If the left and the right were both high, if that logic was not implied using the order, and we wanted it to go in the otherwise stage.
Oh, so you're saying that if left is high and right is high, then you actually want to do the otherwise?
Yes.
You'll have to modify this thing out here. So you can just modify these conditions out here. Okay, so like here you would say instead of and reset and left, you would say not reset and not right and left. Okay, and I guess also you'll probably also have to say and not load. Okay, so you'll have to kind of just list these things out. I mean, basically what's happening is I have 4 inputs, which give me 16 possibilities. Okay, howsoever they get partitioned across these things is depends upon your specification. Okay, usually reset is very clear. Usually that gets the priority. I mean, that's the whole idea of reset, as we discussed last time, brings things to a known state. The others may have priority, or maybe we consider them invalid. So like we could say, if left and right are both high, then it's an invalid situation, and you should therefore just hold the state, which is kind of the point you are making. Yeah. Any other question? Yeah, please.
So we keep designing our system with like, but we get an invalid input where like a bunch of the things are high, something's already gone wrong. In real life, how often do we program a system for redundancy? Because like if something breaks and then no one checks for it, everything breaks.
Yeah, so I think dealing with situations which are nominally out of spec is always tricky. The safe practice is that faced with something anomalous, do no harm. Okay. Now that depends upon what does it mean to say do no harm depends upon the type of system. Okay. And by the way, making systems which are robust in face of not just erroneous conditions but actually deliberate attacks is probably the most hardest problem with sort of complicated systems. And I mean all these attacks that we read about and all, right? I mean, so we read about software attacks quite a bit, okay? And a lot of them happen because, yes, a sane user will never give that input, but hackers do, okay? And by the way, lest you think that these things are just software, you pick any microprocessor, Intel's microprocessor, over time they've discovered bugs and they fix them. So there are errata sheets, and you would be surprised to learn that there are instructions that don't operate correctly, which may, if you feed some data pattern, your processor may go into a privileged mode and a hacker can get it to do sort of things which not normal users cannot and all. So hardware is no different. It suffers from bugs, malware, trojans, you name it. Okay, they're just less well advertised because we all know about software. Relatively few people kind of get to see how a processor works and all. So very challenging. You have to anticipate bad behaviors. So what we dismissed at don't cares actually tend to be often the ones which get exploited, because we think of don't cares as things which were not specified, whereas in reality they become problematic. Okay, any other question? Let's move on. So what we saw thus far is that sequential stuff, we can think of them as either these states we are jumping around among them, and then we can think of them as these data path kind of things where I think of a state as some sort of a variable which I'm manipulating, much like we manipulate variables in a program. And they have their own utilities, okay? And one way to think about it is, if I had a couple of students in today's office hours and we were having this discussion. When you write software, okay, program, what is the state of that program? What information constitutes state of a program, running program? So if you think about it, where all is information stored? It's stored in our variables. So if I say int x, double y, all of those are state. But there is also this hidden state, which is by the program counter or instruction pointer, okay? And we had a brief discussion of it a lecture or two ago. Both of these together constitute the state. One tells us what the value of my data state is. Those are the variables. And one tells us where in the program I am in. Did I take the left branch? Did I take the right branch? Am I in the first iteration of my for loop, or am I in the 10th iteration of my for loop? Those kind of things. So both are state, but one is very nice and elegant, right? I mean, the variable part, we do arithmetic on it, x plus 1, minus 1, increment it, multiply it. The other is this random mess, depending upon things we take left, right, and all. The latter corresponds to our FSM graphs. In the homework, you probably are already seeing that our transitions become soon kind of a mess of arrows going all over. There's no structure to them. Whereas these things that we have been seeing thus far, they kind of are nicely structured. Okay, multiplexer, very good pattern to them. So the data part behaves nicely. The control part, where we are in the program, behaves messily. And usually our systems have both. There's some stuff which is data-like, some stuff which is control-like, and we split them. We make one using FSM graphs, we make the other using data paths. Sometimes the boundary is not all that clear. Oftentimes in our program, we create a variable which really acts as a one-bit variable. Our Boolean variables are like that, right? Or like we want to remember whether input was 0 or not. So we oftentimes declare variables which are not really n-bit variables, but they're really telling us one of a small number of cases. It was 0 or 1, or maybe it was a small number of things, and they kind of begin to act as control. We often say if some condition true, then do something, otherwise not. So we hold them in some variables. So in our programs, we have that structure. Hardware is no different. So real systems, we think of them often as two sequential logic components which talk to each other. One of them we call as a control FSM, and the other we call as a data path FSM. Control FSM we design using the first approach. We think of state diagram, messy movement across different states and all. The data path FSMs are these nicely structured things like counters, timers, shift registers, these kind of things, okay, where we are dealing with n-bit entities where n is large. And the way they talk to each other is that my external inputs, some of them are going to be control inputs, things like reset, load, those kind of things. Some of them are going to be data input, the 32-bit input, for example, okay. And likewise, I will have some control output. These are going to be, again, those 1-bit type outputs. Did I have an overflow? Did the robot crash? Those kind of things. Data output would usually be the n-bit, like 32-bit stuff, that is data-like things. These two are independent sequential logic. They are running in parallel. So this is an FSM and this is an FSM. And they talk to each other. Some outputs of control FSM become inputs to data FSM, and some outputs of data path FSM become input to control FSM. Another way of thinking about when we write programs, I talked about that how I have two kind of states in it. Our variables where we hold arithmetic stuff, and then our program counter or instruction pointer which kind of says where in the program we are. One way of thinking about it is that our arithmetic stuff is sitting down here, is sitting in state registers in the data path FSM, and our program is commanding it. Our program is like our control FSM, and it tells add these two variables and put it into the third variable, multiply them, increment it, all those kind of operations when we write. You can think of it as those are commands which my control FSM is sending to my data path FSM to do stuff. And whenever some funky stuff happens out there, like for example an overflow or an error, or I attempt to divide by 0 or those kind of things, that's the status going out. So that's why you see this term command and the status. So control FSM is like the supervisor. It's jumping from state to state in my FSM graph. It's sending in each state, it may be sending some output to the outside world, but it's also sending some commands to the data path FSM to do stuff like add, subtract, and all. And then this data path stuff is doing that. And so you see out here, this is where our we have this kind of a structure where state register and a multiplexer and some arithmetic or other logic, all of this kind of is a representative data path. And when something anomalous happens, we send out some signal from here. But otherwise, data path is taking data input and outputting data output, and control FSM is taking control type signals, reset, load, left, right, those kind of things, and outputting control outputs like done and those kind of stuff, ready, done, those kind of things. So control FSM tends to deal with sort of a whole bunch of single bit type signals, okay, coming from outside world going to the outside world. Data path tends to deal with arithmetic like numbers, okay, n-bit entities which constitute some to which you can attach some arithmetic meaning to typically, and that's what you are kind of manipulating. Okay, so this kind of split you will often see, and these two, the top FSM and the bottom FSM, are independent pieces of hardware. Both of them are sequential, but they're running concurrently, but they're talking with each other, and they're designed differently. This, like I said, is designed using FISM-like thing, if you may, and this one is designed in this kind of a programming language kind of abstraction. And so the next set of things we're going to see is that how to design these kind of systems which have both elements of doing it. Okay, so let's see. So let's look at an example. So flesh it out further. So Datapath essentially computes the next data state. It updates the variables. Okay, so wherever arithmetic variables in our program or in our system, it updates them. So this is where we end up using arithmetic stuff, multipliers, dividers, counters, shifters, those kind of things. Control FSM is designed using our FISM kind of approach. Okay, a state graph, we are moving among states and stuff like that. Control FSM commands the data path. So it tells the data path what operation to do. Should I increment, should I decrement and all. Okay, so in our programming language, it's things that we do with variables. And inputs and outputs from the external world also get divvied up into that. Okay, so in our, for example, if I go back out here, this in, what kind of input is this? Data or control? Data, right? It's n bit, we are doing arithmetic kind of stuff on it. These reset, left, right, load, these are control type inputs. These are single bit stuff which are commanding things, so they're kind of acting like that. Now in this example, stuff was so simple that we don't really have a separate control FSM, but these are control like inputs. This output is an n-bit output, it's a data like output. Okay, so if I can give you one rule of thumb, things which are n-bit arithmetic type entities or n-bit vectors, they are probably best thought of as data input output. Things which are solo stuff or maybe a small number of bits, they are usually your command stuff. And so let's look at some examples on how these kind of systems get done. Okay, so we are going to design a vending machine controller. Okay, so you've all used vending machines. They usually have some mechanical stuff, dispenses, whatever, potato chips and water bottles and whatnot. There is some sort of a coin slot, you feed coins. Once you have fed enough coins, and then you sort of press some sort of a button to select what you want out, and if you fed enough money, then some sort of mechanism is activated which sort of dispenses the appropriate goodie that you wanted to purchase. So this is kind of this example is a simplified version of that. So it receives three kind of coins: nickel, dime, and quarter, and it has to compute how much you have fed. So what's the total amount of money you have fed. There's a dispense button. When the dispense button is pressed, then it serves a drink. In our particular case, the machine only serves one kind of drink, so just a drink. And so it will dispense a drink if enough coins have been deposited. And then it has to return the chain one nickel at a time. So every clock tick, return nickels. Okay. So that's kind of the abstraction out here. So this is a great example of the kind of task where we need both elements. Okay, clearly we are doing some arithmetic, right? I mean, we have to keep track of money, we have to add them, subtract them, stuff like that. And then we are also doing these control kind of things: dispense drink, monitor a dispense button, activate some sort of a mechanism to dispense the drink. Also the change return mechanism, you have to activate that. So those kind of things. So data path keeps track of the amount. Control keeps track of the sequencing that is happening. Okay, collect money, check the money, dispense the drink, dispense the chain. So data path, control, that's roughly the division of responsibilities between the two. So again, control we design using our FSM graph formalism. This is where FISM kind of stuff becomes useful to look at, or just drawing graphs and working from those. So it has to receive coins, it has to accumulate some, but the actual accumulation of some will happen in the data path. So we are going to, every time we receive a coin, we are going to tell the data path, hey, I have received a nickel, I have received a dime. Actual computation of maintaining the amount of money which the user has deposited will take place in the data path. When the dispense button is pressed, then it has to check whether enough coins were deposited, and then it has to arrange for coins to be returned, and again the data path will come into play out there. So let's look at so this is where you have to kind of put yourself, this is kind of the essence of the design task, like how to divvy it up, and kind of some functions you may find could be better done on one side, some could be the other side. This is a division that we are doing. So this particular controller, what it does is the following. Upon reset, it starts in the state called deposit. So what we are doing is we are going to, at a very high level, we are going to stay in the state as long as the user is depositing money. But we'll keep telling our data path, and that's not shown out here, we'll keep telling the data path every time a nickel is deposited, tell the data path increment by 5. Dime is deposited, increment by 10. So in the data path, there is some register where we are maintaining how much money has been deposited. We don't keep track of it out here because then our number of states would blow up, because many different coins can be done in many different sequences. We get out of the state when two conditions are met. The user presses the dispense button and I have enough money. Now, where would the dispense signal come from? Outside world, some button pressed. Where do you think the enough signal will come from? Data path, right? Because a data path has the information to tell me whether there is enough or not, right? So data path is maintaining that some value and will compare against the cost of a drink and is sending me a 1-bit signal saying, yes, there is enough money, okay? So already you can see that there are two types of signals happening out here, something coming from outside world, something which is coming from the data path. I'll serve the drink. Now serving is probably done by telling some sort of a mechanic saying start serving, and the drink service takes some time, and then once it has dispensed the drink, it will send me back a signal saying I'm done dispensing. The motion, all that mechanical motion is over, so I'll probably get some sort of a done signal from the mechanics, okay? Then I get to the next state. Now I have two possibilities. User had deposited just the exact amount of money, or in which case I would basically say I'm in zero, that I have no money left over, I immediately go back to the initial state. Or other possibility is that I have money left over. Where do you think zero will come from? Data path again, right? Because data path has the amount of money, that has a knowledge of the amount of money. So zero is another signal which is coming from the data path. I have to now dispense the change. Again, there would be some change dispense mechanism. So again, I'll have some sort of a done signal for that. I'll keep dispensing until the amount goes to zero. So I'll do nickel at a time until I have no money to, until I don't have any more money to return, and then I go back to deposit. And I guess there is an assumption out here that there is enough supply of nickels that are there so that I can keep returning the money. So this is kind of a high-level picture. There are a lot of details missing in this thing, but kind of hopefully the gist is clear. That first think of the flow of things that you have to do. Collect money when there is enough money and the user tells you to dispense the drink, dispense the drink. If there is no money to return, go back. If money is to return, then sequence through nickel at a time until you have returned all the change, and then go back to the beginning. And again, we are assuming kind of sane behaviors, that user will not start depositing money while I'm still returning money and those kind of things. So there are simplifying assumptions in a machine like this, but this would be our control side of things. This is a sequencing of operation that is happening. And when designing this, we made assumptions about what the data path has to do. So let's think about it. What all assumptions we made about data path? So one thing we decided, data path is going to give me some signals called zero and enough, right? What else do you think? What kind of commands I have to give to data path?
To add
certain kind of coin input. So here I will presumably get some signals from the coin entry mechanism, coin deposit mechanism, saying whether a nickel was deposited or whether a dime was deposited or whether a quarter was deposited. So I will probably have 3 signals maybe going down to the data path, for example, one saying nickel, one saying dime, one saying deposit, or perhaps we could code it some different way. In the data path, I will need to have some sort of a register for maintaining the sum. Okay, and I will update that register based upon what the control FSM is telling me, whether it is nickel, okay, and then 0 and enough could be obtained from that data path. So let's see how that might happen. So we designed the control FSM based upon what we had in the previous slide, and you see now we have signals called reset, nickel, dime, quarter, dispense, and done. Done is coming from the mechanics. Nickel, dime, quarter is coming coming from the coin dispenser. Dispense is some sort of a button. So this control FSM we designed using this approach. Now what we see out here is things going to the data path. Okay, so let's look at the data path. So firstly, we are dealing with nickel, dime, and quarter, so we can divide by 5 and think of them as 1, 2, and 5. Okay, so how many nickels worth of things? So I have a state register out here, which shows how much money the user has in his balance out here. That's one way of thinking about it. And we also need the price information. So presumably the price information is hardwired in or somehow otherwise set. So what's happening out here now is the following, that I need to update this guy based upon what is being deposited. And I also need to update this guy based upon whenever the drink is dispensed. Whenever the drink is dispensed, I have to subtract some amount from it. Whenever money is deposited, I have to add amount to it. Is there any other case? So under what condition would this amount be updated? So user deposits money, I have to add. Dispense the drink, we have to subtract. There's the returning change. Every time I return a nickel, I have to subtract it, right? So those are the three things. So that immediately suggests that I need to do addition and subtraction. And we saw earlier in the course, I can create a single module called add subtract because I don't need to do the two simultaneously. I'm doing either addition or subtraction. So that begins to give us some sense that, okay, in front I have a multiplexer, but what are the possible values for this multiplexer? Well, I can reset, so that's a 0. I can hold value, nothing is happening, so that's this feedback loop. Or I need to add or subtract coin being deposited. I have to subtract the price when I dispense the drink, and I need to subtract nickels whenever I'm dispensing things. So what we see out here is this mux, which takes 4 values, price and 1, 2, and 5 for the 3 coins, and then feeds it into this out here in this input. And this adder subtractor lets us now take the current amount and add or subtract from it price or 1, 2, or 5, 4 possible values. And if you think about it, this will let us do all the operations we want. Every time a coin is deposited, if let's say a quarter was deposited, then I can set the first multiplexer to pick input number 0, and I can select this adder subtractor to act as an adder, and select this multiplexer to select the middle one, and then that will result in 5 being added to the current state. To subtract, what would you do to, let's say, whenever I dispense a drink, what settings would we have for these multiplexers? Anyone? So I'm dispensing the drink, so I have to subtract the price from this amount. What settings for these multiplexers would you have? So let's start with first multiplexer, the leftmost, 3, second multiplexer, minus, and the third one, middle. Okay, so all these cases can be handled by appropriate setting of the 2 multiplexer and this adder subtractor. Let's try from someone from the left side of the room. I am returning change, so I have returned a nickel. What settings would you have? Any volunteers from that side? Sometime I wish I could move the projector out here so that I can be closer to you guys, but anyone? No, you guys answer too much, unless you have a question.
Yeah. We can do that after they.
Yeah, after they answer. So, want to answer? Sorry to pick on you, but you were smiling, so I thought maybe. So I'm returning. I'm returning a nickel, so I have to update my remaining amount to the user, right? So what would you do? What would you do to the first mux? This? Okay. What about adder subtractor? You will subtract because you're returning a nickel, and here you will select the middle one. Okay. And so all these different scenarios now I have mapped into these settings. So the human art part out here is to figure out the right data path structure. Okay, you have to think of what operations I'm doing on my state variable. And then you have to create a set of multiplexer and logic which will let you do that. And this is not necessarily the only way I could do it. There could be other ways I could structure this. But main thing is that there is a set of operations I want data path to be able to do related to coins being deposited, coin being returned, drink being dispensed, and the assertion is I can do all of these. And then all these controls of multiplexer and this adder subtractor, they are the lines going from my control FSM to there. So in my control FSM, in every state, I have to make sure that these lines have the right value. If I'm returning a nickel, I have to get the appropriate setting. So in this particular case, this is one hot coded, so I have 4 bits here, 1 bit here, 3 bit here. So I have 8 lines going from my control FSM to that side. Okay. Remember we had also talked about that we needed 0 and enough, right? So that you see out here. I take this state and then I feed it into a comparator with the price, and that is the enough signal, and I feed it to a comparator with 0, and these 2 lines I feed back out here, so that's what you see out here also. So these things, so the lines which are going to the mux and the adder subtractor are like commands to the data path, whereas this enough and 0 are the status coming back to the control FSM. And again, kind of your role where you need to bring your design skills is to figure out what is the right data path to pick and what does my state diagram here look like. Okay, but the partitioning, and again, there's no one hard and fast thing. I mean, this is like engineering a system is something that you will have to decide what is the right division, what goes here, what goes here. Okay, so now let's take a pause and do questions. So you had questions.
So I guess it's kind of a weird question, but I'm looking at this diagram. It looks like if we were to run the reset, it would maybe take more than 1 clock cycle to get reflected in the system.
If I do a reset, then immediately this guy will get updated to 0. We'll lose all the money. No, so I don't think I understand your question. So reset goes through control FSM at the next clock tick. So at 1 clock tick, I will observe the reset. At the next clock tick, these guys will get updated, and therefore, and then I guess on the 3rd clock tick, this guy will get updated. So you'll have to look at the timing.
Right. So it looks like it would take us 1 more clock tick to do a reset than it would be to do a regular operation.
Well, same thing out here, right? I mean, when the nickel was fed, this guy will notice it on a clock edge. On the next, and then it will update these things. And the next clock tick, this guy will recognize, and the addition will happen. Same thing with reset. So reset is no different than nickel dime coin.
Okay.
Now I could have short-circuited thing and have a reset signal directly out here also. But the problem is that will not affect this guy, right? So it's probably better to have returned to a reset state out here and then let things percolate.
So it's not necessarily desirable to have reset immediately 0 everything.
That is correct. Again, depends upon the design. So I won't lay it down. You have to think about like what are the ramifications. It goes back to the question which we had kind of like what happens with these unspecified conditions. So you need to think about like what happens when there is reset. I mean, in this simplified diagram, we are gobbling up the money, which is probably not a good idea. So you might want to, if the reset signal comes, you might want to return all the remaining money that the user had. Okay, a sane machine should probably do that, those kind of things. So no one answer that I can provide to you out there. Question?
So is this a more machine in this case? Or
You know, at this stage I didn't specify. This is a more machine, clearly. Okay. You might not want to go. Hello? Okay, he's going to make a quiz. That's right. Okay, I tried. Okay, well, so, and everyone is going to be texting their friends to come. Well, okay, so its upper part is a more machine. The control FSM we didn't specify at all, so could be either.
but would it be better, like you said, because you would have to go through the entire circuit once to update serve and change, right? I mean, you'd have to you take. So once you have the inputs, right,
Mhm.
you have to wait another clock cycle to traverse through the entire, I guess, circuit on top. Then you have to go back into control because it has to move back,
Mm-hmm.
and you have to wait for another cycle to change.
Yeah.
So would it be better just to, I guess, control the logic so it can adjust, serve, and change immediately after? Like when the register.
It's not worth it. Remember, your bigger delays are going to come from this done signal, which is coming from a mechanical side of things. Okay, so a lot of these operations are going to take many, many clock cycles anyway. Okay, I mean, remember, electronics operates at many order of magnitude faster than the real world. Okay, so you use that to your advantage. Okay, so this is the data state. This is kind of like our variable in the programs. And we can look through kind of, if you were to kind of draw a timing diagram of what is happening, then we have all these signals. So you see reset, nickel, dime, quarter, dispense, amount. There's a little bit stuff getting chopped off out here, I think. Okay. Value, sum, next, enough, zero, and all these internal signals. And then I have a series of animations. So see how the nickel went up. So the nickel was deposited out here. So at this clock, at this point, so these are our clock edges, these lines. Okay, we see a nickel being deposited, and as a nickel being deposited, if you look at amount, because it saw the nickel being deposited, so the amount got updated out here. Okay, so there is a 1 out here. Then a dime was deposited, so that added 2 to the system. And therefore we see amount being updated to 3 out here. Next, we see a attempted dispense. So dispense went high, and of course dispense would fail. Let's see, what was the price that I have set out here? So attempt at dispense, but the dispense fails, I think, because there is not enough money here. So enough is still 0, if you see out here. Then 2 quarters were deposited back to back. Amount went up to 13. And it's just walking through this thing. Then now there is another attempt at a dispense. And this time around, the signal enough had gone up. So dispense will actually take place. And after so you see the drink is being served out here. So this is a serve line going high. Then I have to return a nickel. I have to return a second nickel. So a second nickel going down. And then, okay. And then there is the final done, which is coming, and that makes the system go back to the original state. So it's a very complicated set of sequence of things happening, but main point is the user deposited nickel, dime, attempted to dispense, failed because the price wasn't met, deposited 2 quarters, now it attempted to dispense, it succeeded, but I have to return 10 cents. So I serve the drink, and I return the 2 nickels, so there is a sequence of dones which are happening, and then and meanwhile if you see 0 amount, so 0 was, as soon as the user deposited 1 coin, 0 went low out here, and when the amount went back to 0, then 0 flag went high. Okay, so essentially I'll serve the drink and keep dispensing nickel until 0 goes high. And that's what we are kind of seeing out here. So every design is going to be obviously very unique, dependent upon how you partitioned it between the data path and the state machine. And a lot of it just going to come from practice or kind of thinking about what you need to do. So main advice from me would be, when faced with problems like these, first thing is think about the high level sequence of operations you have to do. Figure out what variables you have to maintain in the data path, in this case the amount. And this is best done by thinking in terms of as if you're writing a program. What are my variables and what is the flow of the code? And then figure out what are the commands I have to send to the data path, what operations I have to do there, add, subtract, multiply, divide, all those kind of things, and what is the information I need from the data path. In this case, it was NF and 0. And then kind of design these two things independently. That's kind of the structure that we end up following. I'll do another example to give you some more practice to this, but going back out here, I just first want to make sure any further questions. Okay, let's try to do this example, a combination lock. So what this guy does is the following. There's a keypad, and this keypad, the user uses this keypad to enter digits, and then it presses enter. Okay, so I press some sort of a code and I press enter. This code could be arbitrary length. So this lock has a unique code, which is the unlock code, and if the user user feeds the right set of digits in the right order and of the right length, and then presses enter, then the lock should unlock. If the user presses enter with an incorrect key or an incorrect length key, then lock should not be unlocked. The inputs are coming from a decimal keypad, so these are numbers, so I need 4 bits for the key. And also there is a signal called key valid, which tells me that you can look at the key now. So at other times I can ignore the value of the key. So if sequence was correct, unlock the output, there's an output to unlock the mechanism, so some sort of a signal going out to motor of some form to unlock the lock. To relock, the user presses enter again. If the sequence was incorrect, a busy output is asserted and the lock waits for a time. So the idea is you feed the wrong key input, then the lock will be disabled for a short time so that you cannot do repeated attacks. Okay, it will cause you to wait for a bit before the user can try again. And the other thing is we will assume that this key valid signal and the enter signal, there is some outside circuitry which has made sure that they will only be valid for 1 clock cycle. So every time the user presses a key, so the problem that we usually face is our clocks may be 10 megahertz clock. When I press the key, I may press it for, I don't know, a second or two. So if we were to not do anything, your circuit will see the key being pressed for many, many clock cycles. So usually what we do is we put some front circuitry which makes sure that for a single, when the user presses the key, I see the high signal only for 1 clock cycle. So let me kind of try to explain what is happening out there, because this is something that we see in many systems. So imagine I have my clock, which is a very fast clock. The user presses the key, so the user may press the key like this. So this is the user presses the key. This is my clock. The problem with this is, if I were to look at this in my state machine, I would see that the user has pressed the key at many edges, at this edge and this edge and this edge. There are 3 edges it is doing. So what I want to do is, to my state machine, I want to give a cleaned up signal. So what I would like to give to the state machine is a signal which goes high, let's say out here, and then goes low out here, and then stays low, and only when the next time user presses the key, which is going to go up. So anytime user presses the key, my system will see the key being pressed only for one clock. Okay, how can we design this circuit? How can you design this signal, this thing? So I said this is processed outside by some other circuitry. So my question is, how would you design a circuit which does this? Signal goes high. This is my input, went high, stayed high for many clock cycles. I want to make sure that I'm outputting a signal which is high only for one clock cycle.
You could have like a bit that's like a valid key, like bit that's normally low, and as soon as you use the keys pressed, it goes high for a single full cycle and then goes low again.
Yeah, so how would you design it?
Like when the user key input goes high,
Mm-hmm.
the keys that the like valid is set to 1, and then automatically after one cycle always goes to 0, and will only give a hit set to 1 on like a rising user key.
No, so you're describing the functionality. Could you draw the circuit for me? Why don't you come? If you already know the circuit, no? Okay.
I have an idea. You could make have a finite state machine with 3 states. So you press it and it moves.
Terrific. So yeah. So main thing is this reminds us of what we were doing thus far in previous lectures. This is an FSM, right? I mean, so basically you design a FSM with some states where like in one state the output is 0, another state output is 1, and you transition according to the criterion that we have given, right? So what we can do is we have a state called 0, we have a state called 1. We start out on the state, we move from 0 to 1 when our input, I'm just going to call it in, when in is high, and I'm going to stay put out here as long as in is high, and I'm going to move back when in is low, right? Then I'm going to stay put out here, as you had 3 states for some reason, I don't know why, but okay. But point is, a simple state machine can do this trick. I'll implement it, one flip-flop with some circuitry around it, so that could sit right next to my keyboard, okay? And then what I'm getting out of it is a processed signal, okay, which goes high only one clock cycle.
Wait, but if user key stays high for multiple clock cycles, won't you stay in the output 1 state in that FSM?
Yeah.
Oh shoot.
Shouldn't you
Yeah, you're right.
and have it always return to 0?
Yeah. Okay, I was good. So we go back out here and we stay. No, I should go to another. That's why you have 3 states. Yeah, okay. So
Or you could do yours, but with the output in the.
I'll let you guys figure it out. Okay. Okay, so I stay out here in the 0 state and go back. Okay. The point is you can apply your older FSM stuff to kind of do it. Okay, so some circuitry will do that trick for us. Now I have cleaned up signals. Now let's make our FSM out of it. So we reset, we enter into an enter state. Now I have, the idea is I'm going to keep sitting in the enter state as long as the user is pressing valid keys in the right sequence. Okay, so the idea, so again, this is not a fully fleshed out FSM. Okay, so warning you on that. So I'll keep sitting in the enter state as long as the user is entering keys and they're entering keys in the right order with the right values. Okay, so somewhere, so I'm assuming there is a data path. The data path knows the correct code. The user presses a key. I tell the data path this key was pressed. Okay, and the data path does some comparison or whatever and decide it was all okay. But data path is giving me some signals. Okay, so data path in particular is giving me a signal called length match and key match. Okay, so the idea is that user keys are being pressed. If there is a mismatch, so let's say the password was UCLA. Okay, or well, that's a bad example because it's not letters. Let's say the password was 1234. Okay, and the user pressed 1. So the data part will say key match is good, but length match is not yet there. The user presses 2, key match is good, length match is still not there. user presses 4, now key match is not there and length match is obviously not there. Okay, so there are all these possibilities that will happen. So I'm telling the data path what keys are being pressed. The data path is telling me whether the key match is there and the length match is there or not. The outside world, the keypad, is telling me whether what key is being pressed. So there are some not shown out here, but we know what keys are being pressed. In particular, we know when enter is pressed and also whether there is a valid key or not. Okay, so now one situation is length match has happened. So length match happens means length has matched, and by the way, thus far all the keys were valid. So if at that situation enter is pressed, then I'll go to the open state. Okay, and so this will also ensure, like, if the password was 1234 but the user pressed 12345, then length match will fail. Okay, because user pressed 12345 enter, the length match would fail. So if enter was done and length match is true, then we go into the open state, we unlock, and then we wait for another enter to go back to the lock state. The other possibility is that the user presses enter, but length match is not there. And in which case, we go to the state called wait2, and what we do is we wait here until a timer fires, kind of timer we have done previously. So we have loaded the timer, lets it count down. So I pass some time out here. So we spin, so the timer is giving me some sort of a busy signal. I'm going to wait here as long as I'm busy. When the timer says done, I go back out here. And the third possibility is that the user presses a wrong key. So in which case there was a valid key press, but the key match failed. So I come out here, I go into this state out here, and then let the user press things. Okay, the idea is we don't want to give the user an indication that he's already failed pressing a wrong key. So we are going to wait until the user presses enter, and then again we do the timer game out here. Okay, so we remember out here at the stage that the user pressed a wrong key, so the password we are not going to unlock, but we are going to let the user press enter whenever he or she wants to, and then again we do a timer out here. So there is an implied at this stage there is some sort of a timer we are assuming which is in the data path. So my data path now is doing a few things. The data path is giving me the key match and the L match, and it's also providing me with this timer functionality. Questions on this? Now the hard part, again, I would emphasize is why this way? Well, I had the luxury of copying the design from the book. You won't have that luxury, and the thing is, there's no one unique answer. I mean, you can take this problem and split it many different possibilities. And again, Paul and Salma are going to go through some additional examples during the discussion sections. But this is where your kind of design skills have to come in. Okay. Okay. So now. Let me do a little bit of an animation. So we start in the enter state. If we get key match and L match from data path and enter from keypad, so those are the things that we are getting. So K match and L match are from data path, enter is coming from the keypad. We stay in enter state as long as correct digits are being pressed. So the data path is telling me that. We unlock if enter is pressed and the length has matched. Okay, and by implication also nothing wrong was pressed thus far. If an invalid key is pressed, we move to wait 1. So in wait 1, all we do is we are going to wait here until the user has presses enter. Okay, so we don't want to give user any indication. When we stay there until the user presses enter, and the other possibility is if enter is pressed but only part of the sequence was matched, then also we kind of move out here. Okay, and then in wait 2 we start a timer, wait for it to be done. So what we'll do is in wait 2 we are going to tell our timer start running and then wait for a done signal from the timer. So we are going to just spin out here, waiting for a done signal from the timer. And then once we are done, we go back to the enter state. So that's going to be the sequence of things. So let's look at the data path now. So we already see that some functionality is going to be required from the data path. Data path has to know what the real code is, it will need to compare against that real code. It will have to figure out the length, has the length matched, and it has to have a timer. Okay, so that begins to give us some hints. So the data path in this case is going to be, firstly, I need to have some sort of a memory where the code is put. Okay, so we are going to use our ROM, which we have done many lectures ago. Anyone recalls what a ROM is? Yeah, not the expansion. What does it do? It's a table of values, right? I can index into it, so that's the input address, and it gives me the output. Okay, so so the idea in this ROM is the following: that I will probably have some upper limit on the length of the passwords I'm going to allow. Okay, so let's say the password I'm going to allow could be up to 5 digits. Okay, so that means I have to account for I'll need a ROM where it's kind of a table with 5 entries: digit 1, digit 2, digit 3, digit 4, digit 5, or something longer. So those are going to be my addresses, and then the output is going to be the digit in that location. So input is the index to the table, output is what is in that location at the table. So in my example of 1, 2, 3, 4, n is going to be 2 bits because I have 4 digits max. That's what I'm allowing, let's say. And then code is 4-bit. Why is this 4-bit?
The representation of the number.
Digits, right? BCD, binary coded decimal. Okay, so that's the ROM. So this remembers the code. Then what's happening? Well, the user has to press the key. So I'm going to compare the key against whichever current the value in the password at the current location. So I need somehow something which tells me what the current index is. And that could be done using a counter that we have seen previously. We start the counter at 0. So at reset, I make the counter 0. And every time a key is pressed, I increment it. Okay, so this signal could come, for example, from our control FSM. So this index is going to go through 0, 1, 2, 3, 4. Every time the user presses a key, this index is going to go up by 1. And therefore, it will read the ROM at the right level and tell me what the correct code is. And I'm going to use an equality checker to check whether the key matched or not. Okay, so this part is basically saying if as the user is pressing keys, it's going to match against those and see whether it works correctly or not. The additional thing I have to do is to also see whether the length is matched or not. So this length is also something which I hardwire in, that is key and length are sorry, the correct length, which is whatever is for my password. So I feed that in. So password is stored out here, the length is an additional variable. I do a comparison, and I send out a signal called lmatch. And then finally I need a timer which I can load with a value. I can tell it whether to start running or not, and whenever it is done, it is done. Okay, I think I have, yeah. I'm just trying to see why do I have an M bit out here. But this is a timer which we basically say start. Whenever it finishes, it gives me a done signal. So the data path in this particular case is, as you can see, all the 3 functionalities we wanted: whether the correct key is pressed, whether the length has matched thus far, and whether there is a done. All of that kind of follows out of it. And then we, okay, so all of that has happened. So we take this stuff, we connect it with our FSM, and then we have our overall kind of design. That's kind of the idea out here. Okay, so in summary, these kind of systems, I basically faced with a design. The very high level thing you have to do is to decide what are my variables and what operations do I do on them. That's your data path. How do I sequence those operations? That's my control FSM. It's kind of like when you're writing the program. You think of what variables do I need, and then what is the flow of my program. The flow of your program is the control FSM. The variables you need and the actual instructions you do, addition, subtraction, and all, that goes into Datapath. That you and you have to play with it a little bit upfront as to which one is what strategy is going to work the best for you. Then you design the control FSM, get the sequencing right. Your control FSM is going to send some signals to Datapath and is going to get some signals back from the Datapath. And then you go and design your Datapath. Okay, so you'll have a register with the registers potentially with variables that you are maintaining, and then operations that you are doing on them, addition, subtraction, all those kind of things that we saw. And there is no one right answer to this. And in fact, in simple problems, it may even be, you may say, there is no Datapath. Everything is done using control FSM. Or the other way around, I can do everything as a Datapath. I don't need a control FSM. But typically, you will find that you kind of need to do both. Some data, some control, and sort of figure out what is needed. Now, what is a computer? Okay, a computer is also exactly the same way. There is a control FSM and there is a Datapath. The difference is you are not designing the Datapath; it's given to you. But you are writing only the control FSM. That's your program. Okay. The data path in a computer is fixed, so that is defined by the set of instructions that a processor has. Like it can do addition, subtraction. It gives you the registers which are already in the processor. So your program in a standard computer, you are only programming the control FSM, and you are making use of the data path as is given to you. But the data paths in computers are designed to be very flexible. They support a whole bunch of operations. They have a whole bunch of registers. So there's plenty of space and plenty of operations, and then you are just kind of orchestrating them. But in problems like these, where you have to design both the data path and the control, they tend to be more complex, but also more interesting in a way because you have freedom to do both sides there. So, questions on any of this material? Have any of you seen this kind of stuff in, I don't know, CS33 or these kind of things? Anyone? No? Yes. Okay, I see grand silence. Oh, question.
For the ROM,
Yeah.
That's a 4-bit ROM.
Yeah, in this particular case, the ROM has, each location in the ROM has 4 bits. The number of entries in the ROM, what this N is going to be something in any given design. I've not specified it out here, but that dictates the maximum length of the password. Right?
So the ROM is storing all the possible.
No, ROM is storing the password in sequence. So if the maximum password is, let's say, 32 digits, then N is going to be 5. Okay?
What happens if the user puts in more digits than there are in the actual code?
So we are going to wrap around,
Okay.
right? And it will, so I'm saying, trying to think whether that creates a vulnerability. I can see a problem happening if the user feeds too many things, and then it.
The length will still work. The length batch will come up as not the same.
No, because this will also wrap around. Okay, so but the thing is, user is not getting any. I guess the idea is okay. So what might happen is the following: a failure of the following kind can happen. Let's say my password was 1234. The user presses 5555 or whatever 55551234. The system will unlock.
Wouldn't the first 5 be incorrect with the first command?
But okay, you're right. Yeah, so it will work. Yeah, so first 5 will take me to that state. Okay, so it will work. Yeah. Anytime there's so I guess the only thing is if the user presses 1234 1234, it will unlock. And I don't know whether that's a vulnerability or not, but that's the one case where it will fail.
So if the password were like 3412 and you press 1234 1234, that will unlock it, right?
No. Oh. No, it won't, because if the password was 1234, the user pressed 3. So again, there would be a K match which will fail, and then we'll go to the state out here immediately. So the moment there's a mismatch, we go out here, right?
Wait,
Wait one. So
So that they would have to hit enter in order to reset the system, right?
Yeah, they'll have to press enter and they'll have to suffer through this timer delay also.
Okay.
Yeah, so that's so I think the only example is if instead of feeding the password sequence, I feed the password sequence multiple times. That's the only condition under which it will still unlock, when I guess you could argue that it shouldn't have unlocked.
So if you wanted to avoid that, you can have like an overflow bit on the counter, right?
Yeah, you can have an overflow bit on the counter, set a latch for that. Yeah. Okay, any other questions on this? Okay, so what I want to do is, I have a, for those of you decided to attend, there's, like I said, and you may choose not to take this. Just pass it around. These are just empty sheets. I want to put up the question on the screen. Okay, so what it asks you to do is, this is material from last lecture. Design a Datapath FSM, which is a 10-bit counter, output 10-bit. It has a reset input that resets the counter, load input that loads the counter, a stride input, which causes, when 0 causes the count by 1, and when it is 1, it causes the count to go up by 3 every clock cycle. You need to write the next state output function and draw the schematic. Okay. I had like 60 of them, so that should be plenty. Okay, give me some art on the file. No. Anyone else with comments? You can use anything.
Can the control bits be like simultaneously active?
Pardon?
Can the control bits be simultaneously active? Like, or is it sort of like only one PI at a time?
Oh, okay. Reset gets priority, then load gets priority, and then only otherwise. Done. Thanks.
Can just write that when incomplete.
That's fine.
Yeah.
No.
One question. So, for example, when you find that, find the whole word, do you stay there or you go back to the beginning? If you already find the word, the match word on question 5.
Which part of the
Like coca or something. Like if you already find that word, COCOA, you stay there or you return to the start. Because the UCL example, you stay there.
Yeah, I think in this one, I'll have to read the question.
I can show it to you.
Yeah, show it to me.
Some of my problems happened yesterday, but after you post last night, I think I incorrectly described the
1 and 2.
Yeah.
So what you can do is just for those two parts, submit that. Just those parts. Okay.
Okay, so okay.
Yeah, you submit it to Salma, right? I mean, what you can do is you can scan it or something. That's probably the easiest, and just email it to Salma and she can attach it to it.
Here, like you really find
Let me take care of this problem.
you're done, sorry.
Okay, thanks.
So if you already find apple,
Yeah, I want to read the question.
okay, thank you.
Is it okay for me to write the output of this as just CL out, like, and then have this be the?
Yeah, that's right.
Okay.
No, it will do it repeatedly.
You do repeatedly.
Yeah. So every time it sees. Okay.
Also, you
So-
would go back.
In your state machine, yeah, basically. Go
Like
back.
if you need C, then you go back to the C.
Yeah, so like let's say I see AAPL, XYZ, AAPL, so that would be twice.
Okay, thank you.
Sure.
Can I get my midterms?
You'll have to come with me after later. Sure.
It's just right to it.
Yeah.
Can you read that? Just not.
I think I can make it.
This question, can I implement a clock that take the 3 times the page than the original clock that does? Can I do that?
No.
Oh.
No, you don't need to.
Is this enough?
Yeah, I mean, looks roughly fine. So.
Okay. And can I get back my
Hang on a sec. Oh yeah, okay. You'll have to come to my office right now. Right? So,
okay, I'll pick it up next time then.
pick it up next time. You can pick it up from TA office tomorrow, or I have office hours tomorrow also, so you can come in the morning. If you want.
Is anyone's office open tomorrow so that I can do my homework?
I will be there in my office, but in fact, I think I have office hours that I have set for tomorrow. So let me see what time do I have. But you can always also turn it with my assistant. Yeah, I have 10 to 11 office hours tomorrow, so you can come during that.
Okay. Thank you.
Sure.
And if we turn in the homework in the box in your
In my assistant.
Yeah.
That is fine. Just drop me an email so that I know I need to pick it up because very few students do that. So,
Okay. Yeah, I wasn't sure. All right.
So can I turn this into you right now?
Okay, for that. Sure.
If I found all of these, can I get extra credit for these too?
Yes.
I think I made a mistake in my.
What happened?
Yeah, I forgot to reset the.
Problems at 3.
Hmm?
For 5F, manufacturing. That
question, the last one. I'm still like stuck understanding the requirement where we have to count number ones on X and Y during the session versus since session start.
It's it is since the equality constraint is since the session started until the end of the session. So at the end of the session, you are going to look at how many X and Y came during the session and whether they were equal or not. Okay. So both the constraints are since the session started, but one constraint, the equality, is only at the end, and the other one, which is about less than 2 or whatever, okay, that is throughout.
Oh,
Okay.
Yeah.
Because obviously both at the end they have to be equal, right? So that's like, so idea is that imagine like the two of us are walking. At the end we are both at the same destination, and in the middle you could be 2 paces ahead of me, or I could be up to 2 paces ahead of you, but we'll never be farther apart.
Okay.
Okay.
What do you mean by next state and output function?
Like the ones which we saw last lecture, which you were not there.
I watched. Are you watching?
You watched it? Okay, so those pseudocode type stuff that we were doing.
Oh, okay.
Okay?
So same question for this one.
Yeah.
Do we go back or stay?
Yeah, you go back.
Okay, go back.
So every time you're seeing cocoa, you output for one.
Yeah, and go back.
You go back. Yeah.
So I've done everything except 5F and G. I just wanted to know
I
how.
forgot to write the output function. Okay, that's all for right now.
How do you go about 5F and G? Is there any one that you've done in the past that is something like that?
Is there any more?
Any sample in class that you've done similar to 5F or G?
No, I mean it's really kind of like, you know, we have a problem, how you're going to solve that kind of thing. Okay, so you have to think in terms of if I had given you that problem and said write a program, how would you do it? Just think of that strategy.
I mean, so we are writing like states here. That's what I'm getting confusing. If it was a program, I would have used say an if statement. Or in this case, I would have used a multiplexer or a quality compiler, something like that. Like I can think of all of those things.
Well, I mean, in a way, yeah. So the example I was, or like the parking lot example. So you need to think of like what is the piece of information which will let you do things. So given the set of the situation and the problem, as you can see that perhaps you need to maintain about the difference between the two, and then reason about that, right?
So the state that we write can not necessarily has to be the state as in reading the current input. It can also be like number of ones and number of zeros. That can also be a state.
No, because there will be too many of them. That's unbounded. So if you take that approach, that how many is potentially infinite, right? But in this problem, you also have this additional constraint that I cannot be more than 2 apart, right? I mean, so you have to exploit that. So you cannot have your state as the count because that is infinite.
I'm having problems on the first summer question. Like I looked at the slides and stuff, but I'm kind of confused about like how do you go about doing this? I know the way I did it's wrong, but
so you make once you have the state table,
right.
Then
That's
the
what I kind of did here.
Right. So the equations then then it is basically so assuming the state table is correct,
Yeah.
then it is basically a Carnot map problem. It's basically a combinational problem. So one way you can do it is you can make the Carnot map. You can for each output. So like you have multiple output. Well, you have I guess you have only one output of the Q, right? But you also have 2 bits of state. So you have three outputs really. Your combinational logic really has 3 outputs. It has Q and the next state, 2 bits of next state. Right? For each one of them, you think of it as a combinational logic, and then using the techniques from the first few lectures.
So we're only supposed to have one output then?
No, you have one output which is this Q, but then you also have 2 bits of next state.
Okay.
Right? So those are also output of the combinational logic, right? So that's the next state logic.
The next state as in like, so like this has two things in next state, that has two things in next state type thing.
No. Since there are three states out here, and I guess I have said that your. Oh, I'm sorry. There's a three. I'm doing a one hot coding, so you actually have 3 bits of next state.
No, this one you have 2.
Oh, this one I have 2. So okay. So in that case, there are 2 bits, and then you have Q, right? So you have a total of 3 bits of code output out of your combinational logic, right? 2 of them decides the next state, and 1 decides the Q. So there are 3 combinational functions in a way out here. And for each one of them, you will have an equation which you can obtain using a Carnot
So you're
map
gonna have
strategy.
3 equations then.
You will have 3 equations. Yeah.
One for Q,
One for Q, one for upper bit of S, one for lower bit of
What
S.
do you use to make the cardinal map though? That's why.
By hand or logism?
I mean, like what are because what do you?
Here, this is your Carnot map. Sorry, this is your state. This is your truth table, right?
Yeah.
So like this is telling you again. I don't know whether it's correct or not, but like this is saying if the current state is this and input is this, then output has some value, right? I mean, so I don't know whether this is your out. Okay, so you have so look at this. Okay,
so wait, is output only? We're only for the output. We're not caring about what B and A do. It's only what Q does.
No, for out. Well, in this case, output is only a function of the state. Okay, so actually output. So this thing actually looks wrong because you have in A0 and in equal to B, right? I mean that is, so your output, because it is a Moore type machine, output should depend only upon the current state.
So output should only be Q. There's only one thing
output is Q, and the next state is another 2 bits of output.
Okay.
Right. So the remember again, combinational logic feeds into 2 things: the next state and the real output out of your FSM. The real output out of your FSM is just the Q.
Okay.
But there is also the 2 bits of next state.
Okay.
For also, so you have to write 3 equations: one for Q, and then 2 equations for the 2 bits of state.
Okay.
Okay. And that will fall. This is nothing but your truth table kind of folded over based upon the inputs.
Okay.
Alright. Okay.
For this problem, can we use like inputs like A, or should we have to use the ASCII?
Yeah, that's fine.
This is fine. And also, does this arrow imply that all inputs will go back to this, or do I need to write all the possible, like not X, not Y?
You can just put a star.
Star means all inputs.
Yeah.
Okay. All right. Thank you.
So what is the parking lot?
Okay. Firstly, anyone still needs to submit because. You guys submitting? Thank you. Are you done? You need to give it. Okay, so what's your question?
So what is the parking lot examples? What is the parking lot examples?
Oh, parking lot example was that if I'm seeking to know whether the parking lot is full or totally empty or something like that, I don't need to keep a history of every car that entered or every car that left, but rather I only need to keep history of the difference between the two.
Oh, so I have seen a parking lot example.